Right. Good morning, everyone. Thank you for the kind introduction. I'd like to start with thanking Hydro, VLIZ, and VLIZ, of course, for the honor of receiving this award. And you'll notice that my presentation is slightly different than the ones you've seen before this. It's not about toxicology. It's not about humans getting sick from whatever is in our water, but it's about drinking water. Because without drinking water, there is no health, and we can't be healthy without safe drinking water. So there's a clear connection between that and human health, of course. First, a short introduction of myself. I graduated as a bioscience engineer from Ghent University in 2012, where I started my PhD on ion exchange-based processes in hybrid water treatment. What that means is I specialize in ion exchange treatment, which means all kinds of treatment, mainly membranes, that are used to desalinate water or remove specific ions from water. And the hybrid part means that we focus on combining different technologies to obtain the most efficient and most sustainable solutions for different treatment problems. Our philosophy is why make it more complicated when you can just use technologies that exist and use their benefits to obtain the best process. So I obtained my PhD last year, and now I'm working as the chair industrial circular water technology at the same department, which means that it's my job now to make sure that whatever happens in academia in our group, at our faculty, at our university, finds its way to industry as well. So communicating our research to industry is one way to do that, but also make sure that we understand the needs of industry and we can translate that into useful research at our university. I do that with the help of VLIZ, an important water company in the Netherlands. And as Michiel also said, I work at the Particle and Interfacial Technology Group under the guidance of Professor Arne Verdiepte. So drinking water. When I say drinking water, this is not what most people expect from that. Unfortunately, this is what a lot of our waterways these days look like. Increasing industrialization, increasing world population have caused great contamination of our fresh water sources. But this is not what we need for our drinking water. When we talk about drinking water, we expect something that looks more like this. The thing is, with increasing populations, we will need a lot more water. By 2050, the world population will have increased to, this is a projection of course, around 9 billion people. Fortunately, the incredible growth rate has dropped quite a bit by then, but still this is a lot of people to provide drinking water for and also to provide food for. Because this means that by then we'll need 70% more food. Now this might seem a bit weird because it's not 70% more people, but all of these people want to live to the standard that we live in. We in the Western world, we have a very high living standard that has not been attained yet in developing countries in Africa, Asia, Latin America, and so on. But all of these people's living standards are increasing, and that's of course a good thing, but it also means that they will need more food, and we will need more water to produce all that food. Now, why do we need so much water for all that food? Well, 70% of all the water that we use goes to agriculture, goes to growing crops and raising cattle and so on to provide for our food. Funny thing is, for all of this, we need fresh water. You can't use salt water. But only 2.5% of all the water on our planet is fresh water. And of that 2.5%, only 0.5% is readily available for use. All of the rest is frozen at the poles, for example. So all of the water that we use has to come from this meager 0.5%. Or we can look at the 97 other percents, which are seawater. The vast amount of water contained in our ocean, our seas, is a very interesting source for drinking water in the future. Now, a lot of countries have already started using seawater as a source for drinking water. In the Middle East, for example, where they are not as fortunate as us to have vast reserves of groundwater or river water for freshwater supply, they've been desalinating seawater for many, many decades. Now, there's one great technology to do this, and this is something that our group has been specializing in for the last couple of years, and that's membranes. So membranes are a semi-permeable barrier that allow you to obtain certain compounds from a solution and retain other ones. So you see 4 different ones here: microfiltration, ultrafiltration, nanofiltration, and the last one is reverse osmosis. And all of them have different, for the first few you could say pores, but different retention potential. So you can see a few things that we don't want in our drinking water on the top of the figure, of course. And these are, to some extent, retained by these membranes. And the tighter your membrane, the smaller the pores, or the denser your membrane is, the more you're going to retain. Now for seawater, of course, we want to retain everything, and especially monovalent, multivalent ions, which are basically the salt that is in your seawater. So for seawater, we'll need reverse osmosis, which is the strictest membrane technology that we have at the moment. Reverse osmosis will retain more than 99% of all salts that are present in your water, and will only allow the water to pass. That's very nice, of course, but it comes with a great downside. Reverse osmosis, as the name says in itself, is the reverse process of a natural occurring process. In nature, when you would use a reverse osmosis membrane, such a semi-permeable membrane, as I explained before, and you would contact seawater with a less concentrated water source, nature will strive to an equilibrium. The water from the freshwater side will migrate through the membrane to the more concentrated side to eventually obtain an equilibrium on both sides of the membrane and have equal salt concentration on both sides of the membrane. The difference in water column height that causes is called the osmotic pressure. The osmotic pressure of a solution is determined by the amount of salts that's in that solution. So for seawater, the osmotic pressure is quite high compared to, for example, drinking water. Now this osmotic pressure is the pressure that we have to overcome to be able to push that water in the opposite direction of where it wants to go, in reverse osmosis. So in reverse osmosis, you have to add a pressure to your seawater to force it through the membrane and produce fresh water. Now for seawater, this osmotic pressure is about 25 bars. That's the equivalent of 250 meters of water, so that's quite high. That also means that if you want to produce water here, you're pushing the water through, you're increasing the concentration here. If you want to obtain a water production of 50%, so if you have 1 cubic meter of seawater and you want to produce 500 liters of drinking water, your concentration will double and you'll need 50 bars. And that only increases further as you push the water through further. 50 bars is about the maximum that we can obtain in realistic and affordable installations at this point. They can go up to maximum 60 bars, which is what you'll need, taking into account the osmotic pressure and losses in your system. So at this point, we can only obtain a 50% efficiency for freshwater production from seawater, which is okay because we have plenty of seawater to go around. That also means that we need a lot of energy. This pressure here consumes a lot of energy. And current state-of-the-art installations demand about 2 to 4 kilowatt hours of energy per cubic meter of water produced. To put that into context, the average Belgian inhabitant uses about 2 kilowatt hours of energy per day. So to have 1,000 liters of water, you use about the same energy as one person uses in a day. That seems, to some people, the most frequently asked question I get is, okay, but 1,000 liters is a lot of water. Why is it such a big issue that we use energy for the same as we use in one day? But 1,000 liters is not a lot. One steak is 4,000 liters of water. If you only account for what you drink and use in your shower and your toilet, then 1,000 liters gets you a long way. But if you account for everything you eat, everything you wear, everything you use, you're not going to get very far with that. Now, fortunately, technology has come a long way. So in the 1970s, the energy consumption was still about 15 kilowatt hours per cubic meter, as you can see here. While now, as I said, we're around 2 to 4. Literature already reports systems working at 1.8. That's about the lowest we are getting at the moment. The thing is, there is a limit to this decrease in energy. There's a thermodynamic limit of energy that you will need to desalinate your seawater. And for seawater, that's about 1.1 kilowatt hours per cubic meter. You can't go below that. You'll always need energy to desalinate your seawater, whether it's through a membrane, through distillation, through any other process. This 1.1 kilowatt hours, you can't go without that. The last figure is just to show that there are also other processes used to produce drinking water from seawater, but they are more and more getting replaced with reverse osmosis because these all ask for a lot more energy, factor 2 to 5 more than reverse osmosis. So this number has increased a lot over the last few years and is still increasing. To tackle the issue of this energy limit, we started thinking, how can we go below this 1.1? And the reason we want to do that is to make this technology available for countries where it's needed, but that don't have the resources to invest this much energy in the seawater desalination. Countries like the Middle East that I was talking about have no issue with this. They don't have groundwater, but they do have plenty of oil, so energy is not a problem. Other countries, such as African countries, India, they do need this seawater, and seawater desalination would help them a lot in their freshwater provision, but they don't have the energy that's needed for this. So, as the title of my PhD already said, we looked at hybrid processes. And there is a very interesting technology that's been developed in the Netherlands a few years back that's called reverse electrodialysis. Now I'll explain to you in a bit what that technology does, but in a nutshell, reverse electrodialysis is capable of producing energy from seawater. By contacting seawater with a freshwater source through a different type of membrane, in reverse electrodialysis, you can use this difference in salinity, or this difference in osmotic pressure, to produce energy. Now if you couple that with reverse osmosis, you can get a system that's much more energy efficient, and that's the system I want to talk to you about today. Shortly on how reverse electrodialysis works. So as I said, they work also with membranes, but a different type. So in reverse osmosis and the other membrane processes I showed you before, water is the preferred solute to pass through the membrane. These types of membranes work the other way around. They don't allow water to pass, they allow ions to pass. They are very dense membranes, but they have a very high charge, which means they attract ions and allow them to pass through to the other side of the membrane. You have two types, of course. You have negative and positive ions, so you also have anion exchange membranes and cation exchange membranes. Now the interesting thing here is if you have seawater, and you have, for example, river water, but any freshwater source will do, and you contact those with these membranes, what you'll get is the same equilibrium that nature strives to will occur here, and the ions will move from the seawater to the low salinity side on their own. That's a natural process. This means if you have a lot of these, usually there are a few hundreds of these cell pairs as we call them, all of the negative ions will move to one side and all of the positive ions will move to the other side, creating a potential difference because you have a negative potential on one side, positive potential on the other. Through reduction oxidation processes at electrodes that you place on both ends of these membranes, you can transform that ion flow to an electron flow. That is then basically electricity. And that is in a nutshell how you can produce energy from seawater. The problem here, of course, is if you have river water or any other freshwater source, you're not going to use that in here to produce energy and then through RO to produce water from your seawater. You can just take this water source and produce fresh water, which is why we don't look at river water. We look at effluent from wastewater treatment plants. At this moment, in many countries, even in Belgium, I don't think you'll find more than 10 or 20% of people willing to drink treated wastewater effluents, even after you've put it through whatever treatment is needed to make it drinkable quality. In a lot of countries, this is still prohibited, and even in a lot of Muslim countries, it's just a religious issue to use this water for drinking water production. So we want to try through this process to give this wastewater effluent a second life and play a role in freshwater production without using it for the freshwater production. So again, now I hope you understand a bit more why we want to combine these two. It has a lot of advantages. If we use impaired water, as we call it, which in theory could be wastewater without any treatment, but we're currently looking at the effluent of the wastewater treatment plant. With the seawater in reverse electrodialysis, you'll produce energy. That energy you can use in your reverse osmosis process to produce then the potable water. But an even bigger advantage is that here, part of the salt from your seawater will already have transported to the wastewater, decreasing the salinity of your seawater and decreasing its osmotic pressure, thus decreasing the energy that's needed to desalinate it in the reverse osmosis process. So combining these two technologies has a double advantage. You produce the sustainable energy needed for the desalination, and you decrease the energy that's needed for the RO process itself. Another advantage that I won't go into detail here, but it's very interesting for oceans as well, is that you always have a brine from RO because you have that double concentrated seawater. But if you lower the salinity here already, this salinity will also be lower, and you'll have a lower impact discharge. Same goes for the impaired water. A lot of big cities are at the coast and discharge their treated wastewater into the sea, causing a big concentration gradient in the seawater, causing ecological issues. By combining these two, your concentration that you're discharging will be much closer to natural concentrations in the seawater, thus causing much less ecological issues. Now we did some modeling to take a look at what the actual energy demand would be of such a process. And of course we looked at the best case scenario first. What if everything works perfect? And that's called thermodynamics. And that gives us kind of a goal that we want to work to. It's the same as with the 1.1 kilowatt hours in per cubic meter for RO. That's our ultimate goal, and you see that over the years we've attained that almost, or we're getting very close. So we wanted to do the same for the RED-RO process. And here you can see the RED recovery. If you go to 1, that means that you have removed the maximum amount of salt from seawater that you can in the process, which in this case is half, because then you reach the natural equilibrium, the same concentration on both sides of your membrane. And here you can see the RO recovery. So how much water do I produce? So now we're usually at 50%. If you put in 1 cubic meter, you produce 500 liters. What we found is that as long as your RED recovery is high enough, your overall system can be energy neutral or even energy producing in an ideal thermodynamic world. With this process, you can actually strive to a process that is both capable of producing potable water, but at the same time also produces sustainable energy. Now we'll already be very happy if we can attain the 0, but this is a very good driver for further development of this process. But the main goal is, of course, energy efficient production of fresh water. Now we did the same, and then we included some of the losses. We looked at current state-of-the-art membranes, current state-of-the-art electrodes and systems, and then we redid our calculations to get a more realistic idea of what the energy demand would be. And here you can see, so the same here. This is the RED recovery, so how much salt you already remove in your RED system. And this is the specific energy consumption. So the dark blue bars are the same as the figure before, what happens in an ideal world. And then the lighter blue ones are a more realistic estimate, what happens if we include losses and inaidealities of our system. And you can see if we only remove 25% of the potential in RED, we are around 1.1. So that's the thermodynamic limit for RO. We can achieve that by a small desalination with RED. But of course we can go further, and then we can achieve about half a kilowatt hour per cubic meter of produced fresh water. So that's a very significant reduction of the energy demand that's currently needed for reverse osmosis processes, and also a very significant reduction below the thermodynamic limits for desalination, just by combining these two processes. This is where I kind of ended my story yesterday, but today is a more scientific presentation, so I'm going to tell you about some of the downsides and how we're tackling those, of course, as well today. One of the biggest issues at this moment is that for RED, the natural desalination process, so this natural diffusion of your ions from the seawater to the wastewater, is rather slow. This means that for if you want to treat a lot of water, you'll need a lot of membrane area, and these membranes are not cheap. This is an upcoming technology. These membranes are used in other processes as well, but these are all still in very much a developmental stage, and not like RO membranes that are being produced by hundreds of manufacturers. So these are still very expensive, which means that for RED you have a very high investment cost. You can, I'm not going to explain this, but here you can see in relation to other processes that we might look at for this hybrid process, in RED you need the most membrane area, and it is by far the most membrane area. So that's an important challenge to overcome. So we looked at how we can balance out the investment cost versus still having this interesting energy efficient process. So as I said, in RED you have slow ion transport, you have a high required membrane area, so a high investment cost. So we thought, can't we push the ions to move faster? How can we make this desalination process go faster just by giving the ions a little push? And that's how we came up with assisted RED. So we are aiding the ions to move a little bit by adding a bit of energy to the process. So not enough to have the ion transport be, no, let me rephrase that. The electricity we're putting in here is still lower than the electricity that would be produced by RED, but we're just giving the ions a push and making them move faster, especially in the beginning stages of the process. And that's something that I'll explain in a minute. So we did the same modeling for assisted RED. So if you look at RO, you have the 2.4, 2 to 4. For RED, in theory, it can be energy producing, but in reality, it's very significant energy savings, as you can see here. And then if you look at the assisted RED RO system, you don't get energy production. You actually put in a slight amount of energy, but you still achieve significant energy savings, and you can still achieve this 1.1 kilowatt hour per cubic meter thermodynamic limit. So although you're putting in a tiny amount of energy, you're still having an overall much more energy efficient process. I know you're all thinking now, this doesn't make sense, but it'll make sense in a minute. We started looking into this assisted RED and looking into what happens to the ions if you do this in your system, because it has been done before, but in another process called electrodialysis, where you desalinate your water using electricity. So you put in a lot of energy to move all the ions out. But we are doing assisted reverse electrodialysis. So what you are looking at here is a graph that shows you the ion flux, so basically the current in your system, versus the applied voltage, which gives you an idea of the resistance in the system. In an ideal world, you get the black line. As your voltage increases, your current will increase in electrodialysis. Reverse electrodialysis has the ion flux going the other way around, because in electrodialysis you work against the concentration gradients to desalinate. In RED you work with the concentration gradients. And then you have assisted RED, where you do kind of a combination of the two. So you work with the direction of your concentration gradients, but you add a bit of energy in the other direction. Now the red dotted lines here is what we expected to happen. These processes are not ideal. You get some losses. One of the most important losses you get is concentration polarization. Your diffusion of your ions through your membrane is not the same as diffusion of your ions through the solutions. Actually, in your membranes, it goes much faster than your solution. So you get a different concentration at your membrane than in your solution, causing deviation of the ideal curve, causing losses and a less efficient system. Especially keep this part in mind. This is what we expected to happen. And then we started doing experiments, and then we saw this. So this is exactly the same graph, exactly the same axis. The black line or gray line here is again the ideal line. And most parts we see exactly what we expected. So in ED, you get this flattening of the line because you go way too high in your current. RED is slightly above the line because of minor losses because your current is much lower. But in assisted RED, our system actually performed better than we expected, which is something that not very often happens when you do research. Usually it works worse than you would expect. So we were very happy with this, but then we also had to find an explanation, of course. So we tried this. This is just with 2 different types of membranes. We've tried it with many types of membranes. We tried it with different equipment, because first we thought there's something wrong with our measurement, there's something wrong with our equipment, this can't be happening. But it is happening, and we found the explanation, which is in the resistance, and then mainly the membrane resistance. As you all probably know, resistance is related to conductivity. It's the inverse. The higher your salt concentration in your water, the lower the resistance, and the other way around. If you use seawater on one side of your membrane and you use wastewater effluent on the other side of your membrane, you have a big difference in resistance. Now, research has shown that the resistance of the membranes is determined by the resistance of the low salinity solution. So it doesn't matter that your seawater resistance is very low. If your wastewater resistance is very high, your membrane resistance will be very high. The good thing is, the resistance of these solutions decreases almost exponentially. So you only have to have a slightly higher concentration to have a much lower resistance. So we did kind of the same experiment, but at different current densities. And the -25 here is about the border between RED, which is on the right, and assisted RED here on the left. And that's the main advantage of assisted RED. You apply a small extra current compared to what you produce in reverse electrodialysis, and your resistance drops immediately. So in RED, the resistance can be up to 3 to 4 ohm square meter, while in assisted RED, bam, you're about 0.25, so it's a lot lower. This is data for different concentrations and different membranes, but they all show the same. The main advantage of assisted RED, and the reason it works so well, is because we get this very rapid drop in resistance, not only of the solution, but also the associated resistance of your membrane. This ideal behavior, we mainly see this at low concentrations. So the F1, F2 are 2 different types of membranes that we tested. We mainly work with Fujifilm membranes, so that's where the F comes from, if anyone's wondering. And then we use different concentrations to simulate our wastewater. The seawater concentration we kept the same, that's about 0.5 mole. But the wastewater concentration we varied, because you start at about 0.01 mole, that's fresh effluent. But then as you start going through the RED process, your concentration will increase. And 0.25 is about the maximum that you would expect in RED, that's when your equilibrium sets in. If you increase the concentration, you'll notice that from the curved, so the more efficient working process, you go to a straight line, which is the ideal line, and then at higher concentrations, you can't really see it very well here, but if you even go further, then we do start to see this upward curve that we would expect. So we notice that, okay, assisted RED is working better than we expected it to, but only at the low concentrations. But that's okay, that only means that we only need to push our process a little bit in the beginning to obtain all of the benefits for the assisted RED process. And that's how we came to the final process that we are investigating now, and we believe could be the optimal process for this hybrid process that we are investigating, which is use assisted RED to just overcome this initial resistance, because if you overcome the initial resistance, your desalination will go much faster, the rate of ion transport will be much faster, and your membrane area that you require will drop rapidly. Once you've done that, you can transfer to RED, which will compensate for any energy that you needed here, but which will dilute your seawater that you can then send to reverse osmosis for freshwater production. And this is the process that we are looking into now. So it has, again, all benefits from the systems that we investigate. Now this looks like 2 different processes, so it looks like overcomplicating the system, but it doesn't have to be. They are exactly the same. You need 2 electrodes, you need the membranes in between, you just need to tune the working of your electrodes. In the beginning of your process, they need to put in a bit of energy. While you go further in your process, they need to get out any energy that you can produce. So in practice, this is just one setup. It's just the mode of operation that changes during the process. This is where I ended my PhD. And now, fortunately, we are working further on that. So this is a Horizon 2020 European project for which we have gathered a lot of collaborators all over Europe, amongst which, very interestingly, VLIZ, where the original reverse electrodialysis was developed. It's called Revived Water, and we are looking at low-energy solutions for drinking water production. It's called Revival of Electrodialysis Systems, because we're not only looking at RED, but also assisted RED and ED, maybe even electrodialysis to replace reverse osmosis, so you can integrate everything into one single system. The project has been going on now for about a year, and the ultimate goal is to build a pilot scale setup and test that in countries where these kinds of technologies are needed. We're currently finishing up the preliminary lab experiments and starting with the building of the prototype. And this one will be tested not only in Europe, but more importantly, I was pretty sure, here, sorry, but also in developing countries where these types of systems are needed. Yesterday someone asked me, where exactly in these countries are you going to test it? Well, here. So I didn't know by heart, but there's a few in Africa. We have, in India we have 2 different testing places, and then we have one in Latin America, in Panama, where we'll be testing. The main thing I want to point out with this project is that we are trying to get our lab experience and our lab findings out into the world, which is why we are collaborating not only with knowledge institutes, but also with memory manufacturers. Abengoa is someone that builds reverse osmosis systems. We have Doikum, we have Faizun. Faizun is specialized in remote area solar panel systems. They want to go and commercialize the system once it's optimized and once the project is over. So that's the ultimate goal. By the end of this project, we'll step out and say, our baby is now ready to conquer the world, and you guys can put it everywhere. So that's it for my part today. If there are any questions or any time for questions, I'll be happy to answer them.